Welcome everybody to our monthly Optimization for All Community Connect event. I'm Leon. I'm from Dutton Lines, the ethical AI researcher there. Normally I organize these events with Deepti, but she couldn't make it today, so I'm helped here. I'm assisted here with by Siva. Um, so welcome. Today we have Professor Abhijit Gosavi speaking for us about reinforcement learning, giving a tutorial. We will have a discussion at the end, so please put your questions in the chat, and we'll finish with a little bit of a roundup, in which we also share following events. The presentation will be around 30 minutes, and after that we'll have the discussion. So for those who are new here, a quick introduction to Optimization for All. We are an educational initiative, but we're also a networking hub, and we are mostly a group of optimization ambassadors, so enthusiasts and also people that are interested in spreading the word around optimization, mathematical optimization. So in summary, we are a place for people to grow together in the optimization world. And then I will ask Siva to introduce Abhijit.
Hi, my name is Siva. I'm a PhD candidate from Cornell, studying with city markets, and it gives me great pleasure to actually introduce you all to Abhijit Gosavi. Abhijit, he's a long-term member of Optimization for All. He's helped out a lot in terms of our community as well. So it's a really great opportunity for me to actually present to you his presentation today as well. He's a professor of engineering, management and systems engineering at Missouri University of Science and Technology. He's also an author of a very good book, Simulation-Based Optimization. It's a book that I also refer to from time to time as well. So I'm really happy that he's going to be giving us his presentation. He's an expert in many different fields, specifically reinforcement learning, which we'll be presenting to you today, but also in simulation-based optimization, data analytics, and stochastic process as well. He's also known for semi-Markov decision process and renewal reward processes as well. So yeah, Abhijit, if you're ready, you can go ahead and present your slides.
I will stop sharing them.
Yep.
Can you see my slides now? Yeah. Okay, all right. Well, thank you very much, Shiva, for that very nice introduction. Yes, I'm a part of this group, which started some time back, but we've all had just a lot of fun working together on a number of projects. But I'm very pleased today to actually present some of the work that I have done with some of my colleagues and students and former students. So I titled it a tutorial for reinforcement learning, but I really want to provide an operations research perspective given the audience that we have. So that was my intention all along when I created the slides. So I'll begin with some quick words of gratitude there's a lot of people I need to thank, but I'm going to keep this short. Of course, gratitude to, the authors of the foundational textbooks on the topics of Markov decision processes and reinforcement learning, but also to two former students who did some exceptional work, Angelo and Capera and Ryan Lawhead, who deepened my understanding of reinforcement learning. Then there's Paul Verbose, who was at that point at the National Science Foundation and has done some seminal work on neural networks, and he helped me understand some niceties of the neural network that allowed me to write my own codes. And finally, my current employer, Missouri S&T, and one of my former employers, Colorado State University, Pueblo, where I wrote the first edition of this book. So the approach that I've adopted in this tutorial is that I'm not going to take the deterministic operations research viewpoint. You can certainly understand reinforcement learning through the shortest route problems and then ordinary differential equations. Rather, in the interest of time, I am going to take a more stochastic route, which is sort of more nonlinear, but more intuitive. So we'll begin with, a quick introduction to Markov chains and then stochastic processes, and then get into averaging via the Robbins-Monro algorithm. So I prefer that because of my own work, but also because I think it's easier to present that, make the discussion more intuitive. So we'll begin with Bellman equations, value iteration, policy iteration, following some of the classical books, and then we'll get into reinforcement learning, where again there's a number of books. So what is reinforcement learning? So it's an AI methodology. We call it an AI methodology, but as you will see, it has roots in operations research, and so it solves a key problem in sequential decision making, the so-called Markov decision process. And the working mechanism really involves an agent that interacts with an environment, which can be the real world or it can be a simulator of the system. And it works through trial and error, generating solutions. So we are all familiar with solutions and decision variables and objective functions. And I'm going to try and frame the problem in that setting. There are many applications of reinforcement learning now. There weren't so many when I was a graduate student or when I started working. But now a lot of industries are using reinforcement learning very heavily, and that includes robotics, supply chains, digital twins, even large language models. Some of them have used reinforcement learning. So reinforcement learning combines a lot of these different things, and is sort of a combination tool. It uses Markov chain theory, simulation, neural networks, statistical learning, and the ability, the reason why it's become so popular now is it can actually solve large scale problems that were, which were difficult to solve in the past. So where does operations research come in? So like I said before, operations research, it's very much an operations research problem. It has objective function, decision variables. And so I'm going to quickly, through some slides, and I'm going to go very quickly because, again, half an hour is, how much time I have. But this is an important slide because this makes it clear, all right, that's my intention, is to show that this Markov decision process is a multi-stage optimization problem, which means there's decision making occurring in one stage and then again in a second stage and a third stage, and it goes on. And a number of stages can be either a finite number or it can be an infinitely long horizon of stages, okay? And so in each stage S, you encounter a state IS. And then you move from IS to IS plus 1 and IS plus 2 and so on. Okay, so S is the stage, and just some notation, not a whole lot of notation, but just some notation. And in each stage, you encounter that state IS, you choose an action AS, also called control. And then because of choosing that action, you essentially move to another state with some probability. And we denote, and that's called the transition probability, the famous transition probability of the underlying Markov chain. And you also get a reward which can be positive or negative. And in reinforcement learning, that reward is called feedback. But you're really looking at a sequential decision-making problem where the stages are connected via a Markov chain, okay? And so like I said before, we have these decision variables. The decision variables are essentially the actions that you choose in every state. And in every stage, you encounter a different state, potentially. And the collection of decision variables, instead of calling it a solution, we call it a policy. It's just a name for the solution where, we'll denote the policy by mu, and mu I will denote the action chosen in state I. And the objective function is just a function like any other function. So I've tried to denote the objective function here in a general format. You're trying to maximize it. You can also set it up as a minimization problem. I'm going to go with the maximization formulation. And it's really a sum of the immediate rewards or the feedback that you get over the T stages, okay? And then that function is up to you. That there's a whole variety of functions out there, okay? And so Putterman wrote a classical book in the 90s, and now he's come up with a new book, which is just as exciting, Putterman and Chan, which is, I believe it's forthcoming next year. But he gives, an extensive taxonomy of different kinds of objective functions. But the two that you see on the top, they are the most popular ones. the average reward per unit time, which has been known to us in operations research for years and years. The EOQ uses it, the news vendor uses it, so we are familiar with it. The other one that we are not as familiar is the discounted total reward, or just usually just called the discounted reward, where you use the time value of money. And both of these are over an infinite time horizon. But you have all these, we'll have these on the website, so you can check this out later. And these are the the different kinds of the precise expressions for the objective functions. Okay, and then we need to get into the Markov chain a little bit, because the Markov chain is kind of a baseline important property that has to hold. If the Markov property doesn't hold, much of this theory falls apart, and you will most likely not get very useful solutions out of using reinforcement learning or dynamic programming. So what does the Markov property say? In this context, in this control theory context, what the Markov property says, okay, is that the probability of transition from a state, for a given action depends only on the current state and the next state. Okay, so for a given action, of course. So because of that, because the probability must depend only on the current state and the next state, you can organize these probabilities for any given action in the form of a matrix. Okay, and these transitions link stages, and they create that underlying stochastic process. Again, the solutions, I'm going to skip this slide, but there's a large number of different kinds of solutions. The one that we are really interested in is called a stationary deterministic solution, or stationary deterministic policy, because that's the kind of policy managers can implement. Okay, but there's all those other classes just as important, because this is a subset of all the different kinds of policies that exist. But I need to explain the concept of policy a little bit better here with a simple example. I'll do that. So, for instance, if you have three states, okay, so it's like three places for the decision variables and two actions that you can choose in each state. Then an example of a policy would be 2-1-2, which means you're choosing action 2 in state 1, action 1 in state 2, okay, and then action 2 again in state 3, and so on. Of course, in real world problems, you have thousands or millions of states. And so, that those are the sorts of problems that are of interest to, in the industrial world. And we'll get to that as soon as we look at reinforcement learning. And so this is the Bellman equation, which is kind of at the heart of all this theory. This theory started with the Bellman equation of dynamic programming. And so Bellman came up with this recursive equation, which I'm presenting for the discounted reward. So you can see the lambda, which is the discount factor here. And what the Bellman equation said, and what his results said, is that if you can somehow solve this equation, then the solution of the equation will lead you to the optimal policy, will essentially help in identifying the optimal policy. And the objective function here is also the VI, the value function. Okay, so that is the objective function. You want to solve for it, and then the solution of the Bellman equation gets you the optimal solution. The Bellman equation is a gold standard in this field. Gold standard in the sense that if you're creating a new algorithm and it's a reasonably small problem with, let's say, up to 50 or 100 states, you should definitely try it out on the Bellman equation and see if you get the exactly the same solution that the Bellman equation would yield. And the reason for that, again, is that it is known to give you the optimal solution. So we can always do that when we have small problems. In large scale problems, we can do it. But if you're developing a new algorithm, you want to test that. And of course, in large scale problems, you want to test your algorithm, benchmark it against existing other heuristics. But this Bellman equation is certainly the foundation of this science. And then in the 80s, reinforcement learning was born. And at that point, two different strands of research. One led to the so-called Q-learning algorithm, which I'm going to explain next. And the other one was the actor critic. Okay, both algorithms from the 80s. And so for that, we need to understand the Q factor related to the Bellman equation. Now, the Q factor is defined like this. the way I've shown you, okay, it is connected to the value function. It's the maximal Q factor. So if you have two actions, and if you're in a state, then you're going to have two Q factors for that state. And a maximal Q factor is really the value function. Of course, if you're minimizing, if your objective function is set up in minimizing terms, then this will be the minimal. Okay, and then if you plug this Q factor back into the Bellman equation here, okay, you get this expression. And then since they are both maximizing, what this leads to is really a definition of the Q factor in terms of the value function. But since we've already defined the value function here, okay, you can plug that back in here, and here you get this Q factor version of the Bellman equation, which is very useful, and that is really at the foundation of Q learning, the most popular reinforcement learning algorithm. Okay, and so this is not difficult for anyone with a background in operations research to understand, but this gives you some of the intuition underlying what's going on. So we call this the Q factor version of the Bellman equation. Some of this discussion comes from the very well-known book of Burtsikas and Tsitsiklis, who wrote the first book on reinforcement learning. They called it neurodynamic programming, but it's nowadays called reinforcement learning. Anyway, the one problem with this equation still is that it has those transition probabilities, which are very hard to find in the real world. In the real world, you have just too many of them. Okay, if you have thousands of states, first of all, with thousands of states, you can't you can't even store these transition probabilities. But even if you can somehow find a way to store them, even what is more challenging is to actually determine their values. And without those transition probabilities, the dynamic programming algorithms do not work. So what Watkins said is that but you can express this Q factor as an expectation. Since it's over PIAJ, it's still an expectation, meaning it's an average, okay? And so what Watkins said is, he said, let's apply this old statistical algorithm called the Robbins-Monro algorithm. That is, again, a very simple idea. He merged it with this, and he developed the Q learning algorithm, okay? So the Robbins-Monro algorithm, what it says is, if you want to estimate the average value, then what you do is you start off with some estimate of the average. It can be anywhere. The estimate can start at 0, it can start at -10, wherever you want. And then you keep using this update 1 minus alpha. Alpha is the learning rate or the step size, usually a small number between 0 and 1. And you take 1 minus alpha times x, and then to that you add alpha times the update, which is the sample. Okay, so the sample in the context of Q learning, this is the sample. And as you can see, the sample doesn't contain the transition probabilities. So what the Robbins-Monro algorithm allows you to do is that it allows you to bypass the transition probabilities, which is really what we want to do because we don't want them. Nonetheless, this algorithm, the Robbins-Monro algorithm, comes with its own issues. But first of all, it has to be implemented either in the real world system, where you're automatically getting the samples, or in a simulator of the system. And so those are, one of the two conditions that have to be met for a reinforcement learning algorithm to work. You either need a simulator, or you have to have the ability to do trials and errors in the real world system. And this alpha is something that is usually not a constant, but all of us have, those who've seen forecasting, exponential smoothing, I think all of you are familiar with this kind of a setting where you're choosing 1 minus alpha times the old value plus alpha times, some update. But that alpha should be gradually decayed to 0. So it starts at a small value, but it gradually should be decayed to 0, meaning it should go down as you do more and more iterations. So this was my attempt at demystifying Q learning, okay? And so this QIA is really the merit of the action in a given state, okay? So every Q factor, you can view it as something that tells you how good that action is in that state, okay? And this RIAJ term, which is the immediate reward or immediate cost, is really called the feedback. Okay, and this is the simple algorithm, the Q learning algorithm. One thing I will say is that some of the simplest algorithms, they almost always become more successful. Is a finding I've found, is something that I have discovered over time, is that the simpler the algorithm, the more popular it becomes, especially in industry, where there's a lot of other complicating factors. going on in terms of the implementation. So how does it work? So intuitively, what this is, this is the feedback. So if the feedback is positive, which means the algorithm, the action chosen was good, then it raises the Q value, okay? And if the feedback is negative, it lowers it. And then it tries different actions in all the states many times. It does several trials and errors, okay? And by the end of the learning or the end of the iterations, it goes to the Q factors that actually come from the Bellman equation itself. So ideally, if you have a small problem, you should test if your Q factors reach the Bellman optimal solution, because then you're guaranteed to have an optimal solution. Okay, and so that's something that is becoming more and more important. This is a diagram that kind of explains how the trial and error process works. So you're in state I, okay, and the environment, which is the simulator or the real world, that takes an action, it generates a feedback, RIAJ, that is fed into the algorithm, which updates its Q values, and then it selects another action, and this goes on and on for several thousand trials before you start getting some kind of a sensible set of values for the Q factors, and then you can implement that policy in a real world. All of us know the dyad problem in linear programming. If you most likely if you've taken a course in linear programming, you've seen the dyad problem. Similarly, in reinforcement learning, we have this, we go through this rite of passage via this grid world example, okay? So this grid world example is like a robot in a small room where, you divide the room into all these small grids. And the robot is starting here, and the robot is asked to find its path to this point, okay, destination. That's the task it's assigned. This can be set up as a Markov decision process where each grid is the state. And in each grid, most of the grids, you can take 4 actions. You can go north, okay, you can go west, you can go south, you can go east. And then in some grids, you can see there's some negative rewards, which means you want to avoid those grids. But you start here and you want to reach this place. When you reach that place, you get a very positive reward of 100, and that's what. And you want to reach that place in the in the least possible time. And this is a nice problem because it has multiple optimum, and so you can try your algorithm and see how the algorithm works. Okay, so in the interest of time, I'm not going to go through some of the other algorithms. Most of these algorithms, as you will see, the actor critic is the other important algorithm. It merges the Robbins-Monro with the modified policy iteration algorithm of Putterman and Shin. The policy gradients have been derived from the actor critics. The Q policy learning is another thing that, again, based on the modified policy iteration algorithm. So there's these 2 strands, value iteration and policy iteration in reinforcement learning. And I'm going to finish with one example of industrial applications, but there's many. So Amazon is using reinforcement learning. Boston Dynamics, they're using it in adaptive robot control. Google did a lot of breakthrough research for function approximation. Digital twins, that was an automatic choice because maintenance optimization problems were solved with in the past with classical OR maintenance models, and reinforcement learning lets you solve those large scale problems. So, but in the context of this fraud detection that banks do, okay, they usually have about 3 actions. So whenever a transaction occurs, they can either approve it, or they can decline it, or they can manually review it, okay? And so these kinds of decisions have long-term effects. Obviously, if the customer loses a lot of money, that's not good. If the bank loses a lot of money, that's not good, okay? But there's a lot of fraudulent people out there trying to take advantage of this system. And so you have, you can set up the rewards here, reflecting the profit, loss, the false decline cost, and so on. And banks have a lot of training data. It's the state action reward, state action reward. They can train their algorithms on these. So I'll just run you through some reward functions, okay? So, if it's a fraudulent transaction gets declined, that's a good thing, okay? If a fraudulent, if a fraudulent transaction, a fraudulent transaction declined is a good thing, but, if a fraudulent transaction is approved, that's a bad thing. So you give positive and negative rewards, and then you run your algorithm, And so automatically, what happens is when a new transaction comes in, if it's running on a reinforcement learning setup, it determines what's the best action. Should you approve it? Should you decline it? Should you do a manual review? And so on. Okay. There were some questions on LinkedIn, and so I decided to. By the way, this is also called delayed rewards. All of these problems are delayed rewards, meaning when you choose an action, the effect of that award can become obvious many stages later. Okay, which is what differentiates it from some of our regular linear programming, or this is a multi-stage problem. So the delayed rewards is an important concept. If you want to use reinforcement learning in supply chains, I got this question on LinkedIn. Okay, so so Amazon is using it for inventory control, and a bunch of other firms are also using reinforcement learning. Grocery store chains are using reinforcement learning. One thing you have to remember, to make reinforcement learning work, okay, you have to define the states such that the time between successive stages is significant, because what that does is that ensures that you have the feedback is meaningful. Okay, and that because the reinforcement learning algorithm, unless it gets meaningful feedback, it can't distinguish between good and poor actions. Now, having said that, you can't violate the Markov property. If the Markov property is violated, then you don't get robust policies, and it's very difficult to implement them in. And the third thing I'd like to say here is that anytime you have a threshold kind of policy, like the min-max policies, that we are all familiar with from supply chains and production planning, okay, those kinds of policies can be relatively easily learned with reinforcement learning. So if you can set up your problem in a threshold setup, then those are the sorts of policies that you can um, solve. And the last issue that I'll quickly mention here, I think I have a minute or two left here. The step sizes, the learning rates. If you use that famous 1/n learning rate, that becomes problematic because n becomes very large, and then there's round off errors setting in. Alpha is almost zero. It doesn't work. What has worked for me is this Darkin Chang Moody, the surge then converge rule has worked well, or simple rules such as a plus b plus n, where a and b are large numbers. Okay, those kinds of learning rates work. Exploration is something I couldn't cover because, in the interest of time, it's been discussed extensively in these books. Function approximation, of course, you need to do that well. That's become very good after all the work Google did with the deep learning. And that has, but I would still recommend using a nonlinear function approximation. The policy gradient algorithms are also pretty popular. I haven't had a lot of success with the policy gradient algorithms, but that's just my experience. But there's a lot of emerging directions in reinforcement learning. In the energy sector, reinforcement learning is being used very widely. There's exciting applications there. We also need more stable function approximation. Then there's these multi-chain problems, of interconnected systems, hierarchical decision problems, where these are complex problems. Putterman has discussed multi-chain problems extensively. These are certainly areas where researchers could look at new problems. And then I'll stop here with my last slide. So reinforcement learning overall, it's usually a stochastic problem. The Robbins-Monro algorithm is a good thing to understand. It's important to understand it if you want success with reinforcement learning. OR really provides the mathematical foundation. RL adds the computational power. These two fields come together. In my opinion, we should use reinforcement learning for good things, for saving the earth. And I'll just end with that message here. You can use reinforcement learning for remanufacturing to reduce carbon emissions, for improved disaster response. Reinforcement learning is a very powerful approach. It can solve problems that were considered extremely complex. For instance, some reinforcement learning agents have been able to defeat chess players, master chess players. So that's a very complex task. And so reinforcement learning has the ability to solve some problems that were considered almost impossible to solve a few years ago. But it's produced major breakthroughs. So I think we should be very careful with how we use these techniques. And with that, I will stop. Thank you very much for this invitation once again. And we will open this up for questions.
Thank you so much, Abhijit. It was very quick. You went through it very quickly.
Yeah, I mean, I wanted to finish it in half an hour, and but the slides, will be there. And yeah, my goal was to, sort of give an introduction. I hope it was clear what I said, but
I think it was, and there's people asking to get the share the slide. Someone is sharing that they've never learned so much in such little time, which is very.
oh, good. All right. Okay. Yeah, the slides we are going to share on optimization for all websites, so that's not a problem at all. I think all of you who are here, just join us. We're an exciting group, mostly very young people, unlike me, mostly young people, and at the start of their careers, and we are really thrilled about operations research. So we'll definitely make these slides available for free. Um,
Yes, and we
and
also recorded the session, so we share it as well.
yeah,
I have definitely yeah, I have some questions. If anyone has a question, please put them in the chat. You can also just raise your voice right now. I already see the first question coming in from Stefan de Koning. Question: how would you approach multivariables with this approach?
how would you approach multiple variables? Um, So the multiple variables, if you mean the variables in the states, yeah, the states can be the state is can be a vector, so it can have multiple variables. In practice, what we do, we usually use something called function approximation, which I think I just briefly touched on. Okay, so you would need to use some kind of a neural network to combine all those variables. Okay, and extract the information from all the variables into something we call features. Okay, so Bertzikus has discussed this extensively in his book on how to gather features from the variables, and then those feature space, you should really ideally use the feature space when you're designing that, when you're using the algorithm. So theoretically you can have multiple variables, but from the variables transform that into features for this state, and then that typically in my experience what I've seen is that that makes a huge difference. You have to recognize those features, or there are some approaches to do automatic feature recognition that usually doesn't work well. So for instance, in the chess example, those features were designed by a human being. So you design those features. So they are like features are like, um, attributes of the state. So you combine them into perhaps just one feature to reduce the dimensionality. Um, but the one thing I'll quickly say here is with reinforcement learning, there's, you shouldn't give up very quickly. Okay. Just because one feature, set of features doesn't work does not mean the algorithm is doing badly. Okay. You should try with a bunch of different features until you start seeing success with the algorithm. Now, how do you know if the algorithm is successful? Because in large scale problems, we don't know what the optimal is, right? There's no way. So what you have to have almost always is a benchmarking heuristic. Most industrial problems, we have something else. Someone solved that problem. They have a benchmark, and that you should compare the performance of your algorithm against that. And so yeah, that's pretty much what I'll say. Yeah.
Thank you. If that doesn't answer your question, Stefan, please ask another question. The next question is from Manuel Bolivar. Do you have any recommendations on libraries, packages in Python or Java that abstract some of the complexity of implementing RL models, reinforcement learning models, in a production environment?
Okay, yeah, I think that's a very good question. Python has a bunch of libraries, um, and you can certainly look at those. Okay. Python has some excellent libraries. A lot of people have solved reinforcement learning problems. So my recommendation would be to look at SymPy and all the reinforcement learning libraries. Now, having said that, I will also tell you is that don't ever do anything like a black box. Okay. My personal preference is to not use any of those black boxes. Write your own codes, because the learning rates, if the learning rates, one set of learning rates might work well for one problem, they do not work well for another set of problems. Okay. So the learning rates, the exploration rates, the function approximation, which is where you have to write your own neural network, or at least use some existing code for a neural network, that is where I would be very, very careful with these built-in functions. Because that's when, people start seeing a lot of failure. And I've seen people saying, oh, my reinforcement learning algorithm didn't work. Well, you used a 1 over n, if you use 1 over n, or you use a linear function approximation when the value function is clearly, the Q function is clearly nonlinear, then you are not going to be successful. And so some of those failure stories are emerging on the reinforcement learning. You need some patience. It's something that has been able to beat the human chess players. It's a very powerful approach, which is not surprising because it's rooted in that Bellman equation. Nonetheless, to make it work in practice, you have to do some work on that. So, yeah.
So
Yeah, Python, I would start with Python for sure. Yeah, a lot of SymPy libraries. Yeah.
SymPy. Thank you. And just because the question is also how to extract certain complexities. If I can summarize you, you're also saying those libraries can abstract some of the complexities, but also some of the complexities are just not to be extracted, and you should do some of the work.
Yeah. Very good. Yeah, yeah. And I'll quickly add to that, some of the libraries, they solve very simple problems like the grid world problem I showed you. Now if you look at an inventory control problem that Amazon is trying to solve, or a digital twin, those problems are way more complex. They don't have multiple optima. So yeah, so I would start with them, but it's a process and you gradually start understanding your problem. Definitely try a benchmarking heuristic and see how well it's doing. And when your algorithm starts outperforming that benchmarking heuristic, that's when you know you're getting success.
Yeah. So it's patience and trying things out, but also some strong. But I also see, Manuel, that Tom Cools has also just given a little list of libraries in Java. So then the next question is Crispin. I hope that I'm saying your name correctly. There you are. You're also. I see you on the. You can ask your question yourself, please, if you feel like it.
Yeah, so my question is, so in the real world, time obviously is continuous, whereas things like Q-learning requires a sort of discrete time step. Do you have a good rule of thumb for picking that time step, especially when the actions may have delayed or different delays of when they take effect?
Right. That's a good question. So I believe the question you're asking, Crispin, is that, how do you discretize the time? Right? Is that a question? Yeah. So how you discretize the time, that is something I experienced in the airline revenue management problem that we used to solve, was like a classical problem where we had some existing heuristics from industry that the airline industries were using. So again, you should try and discretize the time in a way such that, I was trying to explain that in the context of supply chains also, try and discretize the time so that there is some meaningful feedback coming in between the time instants. So if that feedback isn't meaningful, then the reinforcement learning algorithm doesn't really react well to the feedback. So that's but if you try and break down your problem where you can extract the feedback and see, okay, this produced a really bad delayed reward, this produced a good delayed reward, okay, and then when the algorithm starts seeing the delayed reward, that's when it starts taking the Q values to the Bellman optimal Q values. Although we don't know what the Bellman optimal Q values are, but just having that idea in the back of your mind is very helpful, because in the end, there is a very solid theory for it. But that's a very good question. That's what causes a lot of the reinforcement learning algorithms to stumble, because the time is continuous and you have to discretize it. And how do you discretize it? If you just go with the theoretical assumption that time is continuous and you're taking feedback every second there is a change, that may not yield the best possible algorithms.
Could I quickly ask, because I can imagine that there's also different, like in the fraud example just now, there's multiple different rewards or penalties that you talk about. And I can imagine that each of these are also discretized in a different way.
Yeah. Well, this is, go ahead.
No, I mean, I would, if you would like to share something more about that.
Yeah. So this is very subjective. And in this case, time is not an issue because, this is every time a transaction occurs, you have to make a decision. So when a transaction occurs in real time, the banks are making a decision. Now, if they have to have a human being there, they will not be able to do it. There's millions of transactions occurring, so they have to have a computer. Nowadays, they have a computer agent that's monitoring the transaction. Okay, and so what banks have done is they have trained their agents on past data. Okay, and so where they found that fraudulent transaction got declined, we said that's good, that happened. So but how do you know whether it's 1,000 or whether it's a -10? So what is a -10 here? That a legitimate transaction got declined, which is also not a good thing, but it's not such a bad thing from the perspective of the bank, because the customer can usually call back and quickly get that fixed. But that's typically how they would do an assignment. So exactly how much this is not usually dollars. These are things this is called credit assignment. They assign it on their own. And so if you assign different numbers here, you can get different policies, but banks usually settle on these numbers before, then they train their algorithms, and then they found that more or less fraudulent transactions don't happen as frequently if they have something like this set up. So here it's not a question of time. Every time a transaction occurs, the agent has to step in and make a decision. But then the good thing is there's a clear feedback coming in because like I think I showed that here, right? So there's a training data from the past where they know when they made mistakes, when they did the right decisions. That kind of data is available, very long, millions of sequences of data from the point of sales data. Just something very similar to point of sales data in supply chains. And from those training trajectories, if you train your algorithm on this, then your algorithm is going to get pretty smart quickly. And then when it sees a fraudulent transaction, now that's based on something I didn't have time to say. So the state here is not just the amount of transaction, it's the history of that person, it's the device on which that transaction occurred, the customer's risk score. The customer is someone who tends to buy things online a lot, then the risk score is kind of high. That can lead to risky transactions, depends on which country the transaction is occurring out of. And so that is the state of the system. So anytime a transaction occurs, all these variables, kind of determine the state. And then the actions, of course, like I said, are the 3 actions. But the reward is where you have to be clever and you have to come up with appropriate values for that.
All right, thank you. I've got multiple other questions, but let's give some other people also the chance. Stelios Nikolakakis, how can we start with RL? Any suggestion to catch up on the fundamentals, especially the mathematical part?
Yeah, so I there are a number of tutorials. I have my own tutorial, but I tried to present some of the basic math here. Nonetheless, there are some tutorials that you can find, and I can perhaps add a list of tutorials to this presentation before we upload it on our website. So you can, I don't think I added. Let me check. In the bibliography, I have some. These are classical books mostly, but I'll add a list of tutorials that you can read. They're mostly freely available, and that should get you started on reinforcement learning. If you have some understanding of operations research, reinforcement learning is not difficult to understand at all. It's a very, very intuitive process for us in OR.
I think that the person that asked this question would be very happy if you would share that. Yeah. So that's very good.
I will be happy to do that. Yeah, I'll update this with a list of tutorials that you can look through.
Sounds great. Thank you. I've got a last question here from Razieh. I hope I say your name correctly. How can I learn reinforcement learning to deploy it in designing solutions methods for solving NP hard problems like vehicle routing problems and designing online data-driven optimization?
Okay, so online data-driven optimization, I can answer that. When it comes to online data-driven optimization, usually you have a lot of training data available. And so you set up your own actions, states, reward function, okay? And then you train that on the data log, just like I showed you in the banking thing, okay? So for data-driven applications, reinforcement learning is becoming very popular, essentially because it works well. And that's one of the reasons why some of these supply chains have started embracing reinforcement learning. Is that if your data set changes, okay, the algorithm can quickly adapt to the changing environment, which isn't so easy to do with other kinds of algorithms. Now, we didn't get into all the details of the transition probabilities, but what that really means is, you're going away from one set of transition probabilities to a new set of transition probabilities, but the change is occurring slowly enough that the algorithm can adapt to the changing data. So that's how the digital twins, where they're using digital twins in industry for maintenance, they are able to adapt to the changing data. Regarding vehicle routing, I'll be honest, it is not my area of expertise. It's not something that I have done a lot of work on. Vehicle routing, I believe, can be solved more easily with some of the extensive literature we have on deterministic optimization. And I have not seen a lot of reinforcement learning applications in vehicle routing. That doesn't mean we can't use it, but vehicle routing, is more of a deterministic problem. And we always start with the Dijkstra and all of that, but it really is less of a stochastic problem. When you have stochastic problems, it adds a whole layer of complexity to the problem domain. And that's when some of these simulation-based or an AI-based algorithms can be very, very useful. Does that answer your question?
The name was Razieh. Okay. Yeah, I think it does. Otherwise, please ask a follow-up question, Razieh. Another
How
question is
start
from
with RL. Okay, yeah, I'm seeing a lot of questions here. I'm not very good with.
No, I will help you. I've already given them. I also see that Siva has just shared a book on it, Razieh. So maybe you can have a look at that, and otherwise also maybe contact Siva. So
Yeah,
the next question.
Sorry, Leon, I just want to add, like we have a lot of resources in the optimization for all website. So the link that I shared is basically a book review that we did a long time ago on BRP, and it's an introductory book on it. So apart from the slide deck that Abhijit will be sharing, we also have a lot of other resources. So if you go to the website under parts, if you click on learning, you would actually see a couple of books that may be useful as well in terms of like answering your questions on reinforcement learning or BRP problems and stuff like that as well. So feel free to actually like look at the website for more information.
Yeah, and I also see the NP hard problems. Yeah, so some of these problems, are NP hard, and but the NP hardness, is not something that, I mean, this because what happens, is that typically the dynamic program can be set up as a linear program. Now, if it's a linear program, then it's not NP hard, right? So mathematically speaking, it's not an NP hard problem. Nonetheless, in the real world, you can't set up the transition probability. So that's what makes these problems very, very intractable. And but that's the other thing. Also, I noticed a comment about oh, thank you. Someone said they learned a lot in a short session. That was certainly my intention here. But yeah, so I would also encourage all of you to join our group because we do a lot of collaborative work. If there are PhD students, they can get ideas for their research. Okay, I see a question here. How can I learn RL to deploy it in? Okay, so that
Yes,
was the
those
one. But
questions. We are at the last two questions, Abhijit. So the how
okay,
responsive. I would actually also maybe quickly add something to what Siva said. It's true, we've got a lot of resources. If you have resources that you think are valuable and you would like to see them added there, feel free to maybe contact one of us and we can see what we can do. And also, if you see something missing, please also let us know that, because then we can maybe try to find something and add it there. So we will do one more question now, and then we go into the little roundup, and then we can go after the hour mark a little bit further with the other questions. So the question here, Abhijit, is how responsive is reinforcement learning to small trending data sets without many repeating seasons? Can it be used here?
Okay, so that's a good question. Okay, so if the data set is set up in a way where there isn't a lot of patterns repeating, okay, the good thing about reinforcement learning is, you can take that data and put it in a simulator, and you can retrain that data several times on the existing patterns. So, so in other words, you're kind of recreating the patterns that exist in the data, and that certainly is something that is going on a lot in the deep learning side of reinforcement learning. So it can be done. However, from the statistical viewpoint, we like to get data that's independent, and so that isn't the best possible scenario. But if that's what you have, then you can certainly try a reinforcement learning algorithm, but create a simulator. In the initial days of reinforcement learning, they were not very thrilled with using simulators. That has changed now, especially after all the success with LLMs. Where a lot of the training is done in an artificial setup. So I would say go ahead and create a simulator for that data, whatever you have, and train the algorithm again and again using different exploration. That will most likely help you find, if there is an optimal policy out there, it will find it.
Thank you. So now we will quickly go to round this up, and then we will continue with your question, Brajwal. I hope I say your name correctly. I will share my screen. Do you see my screen, everyone?
Mm-hmm.
So
Yeah,
just to talk about what we're looking forward to, we have upcoming Community Connect sessions by Ayush Sharma, Ainet Torres, and Carlos Cetina. And I just want to remind again that we changed the time from 3 to 4. And I think that before this sessions, there were a couple of strange things also with the Zoom link, but everything went well, as I can see from the number of participants. But we were trying to fix that. So we moved it to 4 o'clock Central Eastern Summertime. And then Siva will share this slide.
Yeah, we also have a hands-on modeling series. We actually have 3. We have in the past done specifically vehicle routing form, which is pretty cool. 2 weeks ago with Karim Aslan. The next 2 that's coming up is optimization under machine learning lens by Carlos Zetina from FICO. And we also have a professor coming in as well, optimizing rental car revenue, a hands-on intro to revenue management by Chris Garcia. So if you want more details and you wish to sign up to these 2 remaining workshops, feel free to actually go to the website and fill up the form, and you shall receive a Zoom link for those 2 as well. So yeah. Looking forward to seeing you in those workshops as well.
All right, thank you all for being part of this session. If you want to ask Abhijit some more questions, feel free to stay. And otherwise, see you next time.